introduce the optimization of residual deformation in multipass welding with the application of this algorithm. This work was carried out with using finite element method, neural network, and the optimization by B's algorithm. Hence, the introduction began from the background to neural network and BA, and finally is the result. The objective is to minimize welding distortion induced by multi-seam welding in the cold close member. The cold close member is a typical thin walled metal structure with some vertical and horizontal weld seams. The new production of cold close member overtrapped in deciding the suitable welding sequence. As each weld seam has two welding directions, the CCM with 8 weld seams would have more than 10 million welding schemes. In this study, BA was used for searching the best combination with considering the sequence and the welding direction. The fitness function was set as a comprehensive residual distortion at X, Y, and Z direction. Neural network was trained with using the experimental and finite element method results. Hence, it could help to calculate the result quickly, which achieved by the populated combination of BA. First, experiments were carried out to develop the finite element model. Then the neural network was trained with 400 FEM simulation results. Train BR was used to avoid overfitting problem, and the BPN model have 2 hidden layers. For each layer, there has 32. For each layer, there has 32 nodes. And here you can see only dx and dy were considered, as the dz is omitted as it was very small with comparing to the dx and dy when we found the results by experiments and FEM. The training and the testing results showed the developed neural network is stable enough to carry out the work with B's algorithm. As a total combination is only around 10 million. It's not a big project for B's algorithm. Hence, only the original and the typical B's algorithm was used in this study. We also tried the BA with site abandonment technology, but we couldn't achieve the better result. So the original one, we still use the original B's algorithm. In this study, the local searching considers not only the sequence, but also we change the welding direction when we do the random. The continuous 3 weld seam would exchange randomly. Here, the local searching method is quite easy to set, and we think the BA is flexible, and you can change any local searching method quickly with limited code. The best sequence and the worst sequence were both searched by BA in this study, and the result showed that with optimization by B's algorithm, most suitable welding sequence could be decided in the design process. So we have the conclusions. First, B's algorithm is suitable in solving the combination optimization problem. For example, in this study, we deal with the welding sequence, and it's quite easy to try the effects from different local searching algorithm. We also try the local searching method, very similar to the GA. And for the 10 million scale problem, the original BA is enough. And the last one we found in this study, we tried the FEM, BPN, and BA, and it's connected well. And also we achieved the great result. at the previous, we also do the optimization without the BPM, just with the FEM and the BA. And in that stage, we found it costs a lot because each random we would use the FEM to calculate once. It costs a lot. But with the help of BPM, it saved a lot of FEM simulation cost. And the detailed research was contributed into a research paper and published online just this week at the engineering operation of artificial intelligence. If you are interested in this work, I can share the download link. I'm Chao Wang from Suzhou, China. Thank you, everyone.
Very pleased to be participating in this International Peace Algorithm and Applications workshop. And in the parallel session, I want to present some work which we have done to enhance the BEAS algorithm based on neighborhood search and recruitment of bees. This work was done by Arthur when he was doing his PhD with Professor Pham and myself. The outline for the presentation is I will give an introduction and then highlight the aim and objectives, and then introduce the improvements made onto the BEAS algorithm, namely the enhancement based on neighborhood search, and then on the recruitment strategy, and then combining these improvements into one algorithm and applying it onto some benchmark functions to show the results, and then conclude. So optimization and looking for the best solutions is, as I said, it has to be done in two ways. One is to explore, and the other one is to exploit. So on the top, you can see focus is necessary to do the local search, and a wider view of the search space is needed to explore. And there is always a balance. If you do too much exploration, then it becomes very random. If you do too much exploitation, then there is the danger that you can get stuck in a local optimum, or even end up into the situation where you will have a premature convergence. So some ideas for improving is how to balance this exploration and exploitation, and doing like a reward, like a reinforced learning. So when it is going in the right direction, you give a reward. If it is not going in the right direction, then you give a penalty, you penalize. And so this way you can have a healthy balance between the exploration and exploitation. So the overall aim is, of course, we want to make the BEAS algorithm find the solutions more effectively. So although this is done for single objective, this can be also applied on problems with multi-objective situations. So the objectives are going to be how to select the neighborhood search for identifying promising search spaces, and then how to, having found promising search spaces, how to recruit more bees to exploit that flower patch or the particular search area. So let me introduce the enhancement that was done based on the neighborhood search. So what is the problem? Problem with random, if it is too random, as I said, it's going to be ad hoc, and the results you get will also depend on the random initialization process. If you are unfortunate to start searching in wrong areas, then that's not going to lead you to good solutions and in in a relatively short time. So what is the proposed solution? So start search. So right from the beginning, you want to ensure that you are targeting the best locations to search. So you need some kickstart for the algorithm to enable the scout bees to focus on more promising locations. So this is called the early neighborhood search strategy, and this will be introduced in the starting phase of the scouting process. So this graph again shows the idea. So rather than just randomly go everywhere, you want to pre-select most promising areas, search spaces where the scout bees can be recruited. So here we have identified the neighborhood sizes and areas where the search can happen. So exploitation here. So, but that will give you better fitness valued sites discovered to start the global search. So you kickstart the search with pre-selected promising areas, and the convergence to the global optimum then is more likely. So second improvement is having found the most promising areas to search, you want to allow more bees to exploit. What is the problem? The problem with fixed number of bees recruited to the elite patches is not very efficient. You know, if the area has got lots of interesting results inside, you want more bees. And so the proposed solution is to make it proportional. The fitness value of that neighborhood, the promising search area, must be proportional to the number of bees being recruited to exploit that site. So this is called the efficiency-based recruitment strategy, and this will be introduced in the second step. So having kickstarted the search process with most promising patches, then you introduce the efficiency-based recruitment. So this diagram here shows what I mean by recruiting more bees. So this peak here is more promising because if you're looking for the maximum, you know, that's where the maximum is likely to be. And you want here, we have lots of bees going in the other areas, but actually we want to recruit more bees in this most promising area. Okay, so the number of bees recruited for the search should change dynamically, it shouldn't be fixed. And this will inevitably increase the performance of the algorithm. The enhancement-based recruitment strategy can be implemented. The equations to determine the dynamic number of bees is given by these two equations. Okay, and where NEP is the number of bees around the elite sites, and NSP is the non-elite best sites, and NAB is the extra bees that you are going to recruit, whether it is an elite site or if it is a non-elite best site. Okay, how do we determine the number of bees? So here we have like a lookup table, and we use this efficiency rate, ER, to determine how many bees are to be recruited extra for those sites. Okay, so the efficiency rate is split into, it's normalized between 0 and 1, and then it's split into 5 groups equidistant, and if the efficiency is between 0 and 0.2, then no extra bee is recruited, but if it is between 0.2 and 0.4, 1 extra bee, and the other case from 0.4 to 0.6 is 2 bee, and all the way up to 4 extra bees are recruited. So this will give a dynamic way of recruiting more bees based on the efficiency of the site. Okay, so the early neighborhood search and efficiency-based recruitment both combined together. This is the way the algorithm will work. So it will kickstart the search process by finding the little bit promising patches. So initialize population with random solutions and do early neighborhood search for each random solution, evaluate the fitness, and from that you identify the most promising, little bit interesting search spaces. Okay, and then having found those, then you recruit more bees based on the efficiency of those sites. So here I have got the standard or this basic bees algorithm, which we're familiar with. Okay, so initialize, evaluate the fitness, and select the M sites which are promising for the neighborhood search, and you determine the neighborhood size and recruit bees from the hive to the elite sites and find the fitness. So inside this box from 3 to 6, that is your local search, neighborhood search. And then what about the remaining best sites? So elite sites is selected. And so those are M sites, and N minus M is the remaining patches. Random bees will go there, and you have a exploration going on. So you have both. And the new introduced algorithm, the top is the kickstarting of the promising patches. So you place random N bees on the search space, and you have the early neighborhood search for N scout bees, evaluate the data received from early neighborhood search. Having selected those, and then you do the exploitation here. Okay, so this will use the equations I showed you earlier to dynamically change the number of bees recruited for those promising patches. Now, going to experiments and results. These improved algorithm is tested on some standard benchmark functions. These functions are sometimes single objective, sometimes multi-objective. They have lots of nasty constraints and local optimas as well. So it makes it difficult for the algorithm to find the global optimum. So these are selected purposely to see how rigorous your method is. Okay, these are the parameter values which were used. So the number of bees used, 10 for depending on the functions. We change the population size. These are number of elites and non-elite sites, and so on, the neighborhood size. So these are the parameters used. And what about the results? The algorithm was tested and compared with some other algorithms as well. PSO and compared with EA, evolutionary algorithm, and ABC is another bees algorithm. It's called the artificial bee colony. So, and then our basic BA, and this is the enhanced BA. Okay, and these are the average results, whether they found the known optimum and what's the difference between the newly found optimum and the known optimum. Okay, as you can see, the results are not bad. They don't always get best results compared to other algorithms. It depends on different functions. So the message is one size doesn't fit all. You have to see which problems suit your algorithm best. Okay, this is for the timing. Again, you find the quality of the solution by looking at the fitness value found and also the computational time taken to converge. So again, some functions took longer, some functions were solved quicker with the enhanced algorithm. So overall, were the results significant? We did a t-test, and we found that the improvements made were all significant based on the improved algorithm. And there is still more work to do. So in conclusion, the proposed algorithm performed overall, in general, better than the better on higher dimensional functions than lower dimensional functions. And the results were statistically significant. Future work will be focusing on providing memory to avoid site repetitions. Okay, and the more details can be found in this PhD thesis by Asa Imanoglu. So I think that's all from me. Thank you, Chair.
Hello everyone, I am Murat Şahin. I am design engineer and working at Roketsan in Turkey. In this study, we developed the BIS algorithm toolkit for optimization in LabVIEW. I have worked with Professor Pham in this study. We know the BIS algorithm has been coded and used in applications such as C, MATLAB, and Python. Another program is LabVIEW, developed by National Instruments. It's a powerful and flexible program tool that uses the graphical programming language. LabVIEW is used in signal processing, assistance, and also industrial applications. Some optimization algorithms, including particle swarm optimization, BAT algorithm, ant-line optimization, and gray wolf optimization methods, have been coded and used in LabVIEW. It's seen that the BIS algorithm had not been coded in LabVIEW yet. This is the main motivation of this study. BIS algorithm mainly consists of two parts, local and global search. In local search, more neighborhoods are searched close to the minimum values, as in honeybees, while less searches are made in other sites. Random searches are performed in the global search section, and if good values are found, these sites are transferred to the local search section in the next iteration. Before the main algorithm, the problem must be defined. In this section, the eclipse function is shown as an example. You can see the equation of function for two variables, and the LabVIEW code is given in figure. The second step of the algorithm is to generate the first population. The first population is randomly generated within the limit values. It is shown in figure. The x1 and the x2 variables are generated with the random number block. These numbers are sent to the function shown in figure, where a fixed value is calculated. In this way, members of the first population and the cost of the members are established. After the generation of the first population, the local search section begins. The first part of the local search is the elite site search. In this context, a random value is created within the boundaries of neighborhoods and added to the value of the current member. Two different neighborhood methods have been prepared in this program. The first is a fixed neighborhood. In each iteration, a random search is made within the same neighborhood values. The second is the shrinking neighborhood method. In this method, neighborhood size decreases at a certain rate during each iteration. In this way, more precise search can be made with smaller neighborhood values in future iterations. Elite site search code is given in figure. It consists of two nested for loops. In the inner for loop, the best neighborhood is chosen. In the outer for loop, the best neighbor is compared with the current member of the population. As a result of this process, it continues with the best member. In the best site search section, only the limits for loops change. Continuous optimization section has two parts. The first part is test function. In this part, there are 10 different test functions. And the second part is the new function parts. In the second part, the user can prepare new functions. In this context, the following user interface was prepared. From this interface, variable names, equations for the function, limit values, neighborhood size, and neighborhood type can be filled. Many mathematical functions used in C and MATLAB can also be used here. You can see some test results of test functions. The Bayes algorithm can find the minimum values of these functions very quickly. Second part of this optimization tool is combinatorial Bayes algorithm. We used traveling salesman problem as an example. In a traveling salesman problem, a salesperson has to tour different cities. Person starts from a city and returns to it after visiting each of the other cities only once. The aim is to complete this journey with minimum cost. The cost of the tour directly depends on the length of the tour. In classical Bayes algorithm, the first population is randomly generated, as in many other methodstic algorithms. This method is very effective for finding the global optimum in continuous problems. But the number of the possible solutions in TSP is directly dependent on the number of cities and is expressed with n-1 factorial. Therefore, it is very unlikely that a randomly generated route will be close to the optimum route. In this context, the nearest neighbor method has been proposed for the generation of the first population. This method starts from the closest two cities on the map and then goes to the third closest to them, and this process proceeds as follows. In the first steps, a neighborhood matrix was created for each city within the scope of the nearest neighbor method. For each city, according to the distance to other cities, a close by distance ranking is made. In the second step, a random city is determined and method is applied starting from that city. With the first for loop, the randomly selected city and the second ranked city are taken using this method matrix. With the second for loop, after each city is added to the route, the closest to this city is found. In the last step, the length of the route created with the method is calculated. Route and length values are written in the same array. With this method, a much lower cost route is produced compared to the randomly generated route. In this way, optimum routes can be reached more quickly. Local search is different from continuous problems in combinatorial problems. For DSTSP, the locations of the cities on the route are changed with some functions, trying to find new routes with less cost. The order of two random selected cities is changed with the swap operator. Cities are chosen from the neighborhood. The first city is randomly selected and the other city is randomly selected among the nearest neighbors. In the insert function, a randomly selected city is added to a tour. The insertion site is also chosen randomly. After the insert operation, the city duplicated by the inserted city is removed from the tour. In the inversion function, the order between two random selected cities is reversed. These operators are used randomly in each loop, with more numbers on elite site and fewer numbers in the other local search section. The elite site search is shown in figure. The main structure here is the same as that given in the continuous optimization. In the continuous problem, random numbers were selected in neighborhoods, but in this section, the random function is selected. You can see in this page some test results of combinatorial problems. The comparison study was made with other methodistic algorithms, which are the discrete symbiotic organism search algorithm and the adaptive ant colony optimization. For most problems, better results have been obtained than the other algorithms. This paper has presented the development of the Bayes algorithm toolkit for solving optimization problems in LabVIEW. Toolkit enables users to develop their own applications. and Toolkit can be easily adapted to many different continuous and combinatorial problems. And also, it can be used in industrial applications with LabVIEW. Thank you for listening.
Hello everyone, I am Milan from the Indian Institute of Technology, Kharagpur. In this session, my co-author Aryan and I will present a meta-heuristic solution to the green vehicle routing problem using the Bayes algorithm. First of all, I would like to thank Professor Natalia and Professor Pham for their constant support and guidance throughout this research. I would like to start by introducing the green vehicle routing problem. Green vehicle routing problem is a variant of the vehicle routing problem that is relevant for vehicles with a very limited driving range, for example, electric vehicles. The picture on the right gives a very intuitive example of such a problem. We try to find solutions for this using the Bayes algorithm. It is worth noting that although we are using it for a particular case, the idea is much more general. The same algorithm can be used for other problems that can be framed similarly because we are just trying to minimize the cost of traversing a graph with optional nodes. Before moving on to our approaches, I want to mention the related works that we build upon. The green vehicle routing problem was first introduced by Erdogan et al. They tried to solve it using the MCWS heuristic. They also found the exact solutions to their synthetic dataset using the commercial software called Simplex. Our solution method is based on the Bayes algorithm and its variations introduced by Professor Pham et al. A.H. Ismail et al. Reduced the parameters for the Bayes algorithm to 2. We also build upon the works by Masoudi et al. To introduce a hybrid Bayes algorithm with simulated annealing. Costa et al. Addressed the green vehicle routing problem with a genetic algorithm approach based on local and population search. We compare our algorithms with this approach to examine how the Bayes algorithm performs with respect to other meta-heuristic algorithms. Next up, Aryan will explain the method of our experiments.
Our research is mostly divided into the following steps: finding optimal parameters, deciding stopping criteria, running basic Bayes algorithm, standard Bayes algorithm, hybrid standard Bayes algorithm, 2-parameter basic Bayes algorithm, and 2-parameter standard Bayes algorithm, and the genetic algorithm on a few samples and doing statistical analysis of the results. Starting with parameter tuning, we went for the popular grid search, which is widely used to tune hyperparameters of machine learning algorithms. Grid search is advantageous due to its fairly simple implementation and parallel nature. We implemented grid search with multiprocessing, which made the tuning process very fast, despite having so many tunable parameters. We have mentioned the parameters we found after grid search for our problem. The initial temperature of simulated annealing hybrid is usually our initial guess at the minimum cost. Coming to stopping criteria, we are using 60,000 number of function evaluations. The reason behind choosing number of function evaluations over number of iterations is that the meta-heuristics we are using in our work are population based. Number of function evaluations is also directly related to the complexity of algorithms. Said reasons make number of function evaluations perfect for comparison of algorithms. Now, in order to find correct NFE limit, we studied the convergence graph of basic Bayes algorithm on a synthetic sample with known minimum cost. We chose the samples such that the number of customer nodes are in the same range as the samples in the GVRP datasets. We can see in the convergence graph that the basic Bayes algorithm converges at around 40,000 number of function evaluations. We took 60,000 as stopping criteria so as to accommodate other algorithms. Coming to the algorithms, basic Bayes algorithm involves the following steps: generating NS scout bees, selecting NB best bees or sites from the population. For each bee in the best NB bees, sample forager bees in the neighborhood. In each neighborhood, best bee sample becomes the center of the patch. More scout bees are generated. These processes repeated and the solutions keep getting better. Coming to standard Bayes algorithm, the key changes here are site abandonment and neighborhood shrinking. For each batch, now we declare an iteration limit in addition to the neighborhood size. In each iteration, iterations left is decremented by 1 and neighborhood is shrinked by a factor of alpha. If best sampled B is better than the center, neighborhood size and iterations left are reset to their initial value. And if a patch hits 0 iterations left, it is removed from the population, as we call it site abandonment. Now we talk about improved Bayes algorithm. This uses the concept of simulated annealing. Instead of replacing center B by sampled B, when the latter is of better fitness, center B is now replaced by sample B by chance. The probability of this event is proportional to the difference between cos of center and sampled B. For situations where sample B is better than the center B, the probability is 1. This idea is inspired from spontaneity of reactions depending on difference of free energy divided by temperature. Here, lowering temperature makes algorithm more and more deterministic, whereas increasing temperature allows for suboptimal Bs to be chosen in order to avoid local minima traps. The temperature is decreased linearly with iterations so that good solutions are not lost.
This is the flowchart of the statistical tests that will be covered in the following slides. We start with statistic descriptive and then move on to more complex statistical tests. For our analysis, we use 3 datasets, namely sample 1, 2 and 3. This is the box plot of the results of 100 independent runs. It shows that the basic Bayes algorithm and the 2-parameter basic Bayes algorithm have the best results, that is, the minimum number across all 3 samples, but we need to test statistically. The first step in the statistical test is the normality and homogeneity test. The results show that the significant for several algorithms is not following a normal distribution. The same is with the homogeneity of variance test. Therefore, we use non-parametric Kruskal-Wallis test to find the best performing algorithm.
After the normality and homogeneity tests, we apply non-parametric Kruskal-Wallis test and show that the null hypothesis is rejected for all samples. This indicates that there is a significant difference between algorithms. In order to better understand which algorithms are significantly different from a statistical point of view, we continue to the post hoc test. We conduct the Dunn-Bonferroni test, which tells us about pairwise differences between the algorithms. The test shows that the basic Bayes algorithm and its 2-parameter version are the best performing algorithms for our problem. The experiment used Python for all Bayes algorithm variants and Java for genetic algorithm. Results of 100 runs for each algorithm is collected, and the experiment shows that basic Bayes algorithm and its 2-parameter version achieve the best results, which is the minimum route distance in this case. The statistical test shows that the basic Bayes algorithm and its 2-parameter version outperform other algorithms.
With the economic and environmental changes, there is a shift from traditional fossil fuel powered vehicles to alternate fuel vehicles. However, the maximum travel range of an alternate fuel vehicle is usually less than that of a traditional vehicle. Hence, clever techniques have to be integrated to balance the trade-offs. We propose a meta-heuristic algorithm to micromanage fuel and route planning. From our experiments, we conclude that the Bayes algorithm can provide the best solution for the green vehicle routing problem. The basic Bayes algorithm and the 2-parameter basic Bayes algorithm outperform other algorithms. Future works will focus on using the 2-parameter basic Bayes algorithm for other datasets because it needs only setting of 2 parameters while basic Bayes algorithm needs 6. With this, we come to an end of our presentation. Thank you for your attention.
Greetings everyone, I'm Pratyushkar and I'm here with my co-author Vaibhav Jalani to present our work on the estimation of battery state of health using a ternary Bayes algorithm. The contributors for this work are Vaibhav Jalani and me from the Indian Institute of Technology, Kharagpur, Ms. Natalia Hardono from the University of Pelita Harapan, who is also pursuing her PhD from the University of Birmingham, and Professor D.T. Pham himself. So before discussing our work, let's first talk about the problem itself. As we all know, lithium-ion battery performance deteriorates over time. Evaluation of lithium-ion batteries performance degradation is critical for ensuring operational reliability. You can see a general relation of the capacity of a battery versus the number of charge cycles it has gone through. The SH of the battery is defined as the ratio of the present capacity to the capacity of the battery when it is just manufactured. It is observed that if SH falls below 80% of its initial value, the battery is said to be unfit for use. The performance of a lithium-ion battery is directly reflected by the battery capacity produced by fully charging and discharging a battery cell. The reason the battery capacity deteriorates is the increase in the internal resistance of the battery cells. Several factors such as temperature, age, charging, discharging cycles, operational voltage, operating current affect the state of health of the lithium-ion battery. Moreover, other parameters such as the type of charging used, the extreme climatic conditions also affect the SOH of the battery. The various factors that affect the life of the battery are calendar aging, external atmospheric conditions like temperature, humidity, increased resistance due to manufacturing defects, an extensive number of charging discharging cycles, also known as cyclic aging, and anode cathode degradation due to battery aging. Another major roadblock in real world applications is that the battery is charged and discharged dynamically. This makes it difficult to determine the true capacity of the battery and to assess the battery's performance's decline in order to assure battery safety. So basically, we want to estimate the future battery state of health. That is the future of this curve. This work is regarding the simulation of a lithium-ion battery and the estimation of its maximum available capacity. We use the digital twin. Digital twin is basically a digital replica of physical assets derived from real-life data collected using various types of sensors and monitoring technologies of the asset while in operation. It often means that an analytical data-driven model, that is the twin, is built to analyze, update, and manage the performance of its physical counterpart. This work related to the part of digital twin in the application layer using a real data and modeling it. The method makes, our method makes use of an improved ternary Bayes algorithm, also called as BAA22, for regression. It was initially developed by Sultan to be applied in NLP problems. Basically, it works by simply examining three distinct solutions in each iteration. BA3+ combines three Bayes' collaborative search to determine the best set of trainable parameters for the deep learning architecture. To identify the optimal set of trainable parameters for the proposed deep learning architecture, the Bayes algorithm utilizes global learning with explorative search, which achieves faster results without being trapped at local optima.
Digital twin can be understood as a virtual object that represents subsystem. The twin is expected to respond to input variables in the same way that its physical twin does. So we can say in a way that the most important feature of a digital twin is that it can simulate the physical features in a digital context. So the basic digital model represents the production network and the structures relevant data points according to the universal object data types. And it is usually created using the data stored in the existing information systems of a company or its partners. So it facilitates the digital twin's continuous updating and enables an archiving function that allows the application layer to access the network's older states. And the application layer consists of multitude of different models that are modular and serve various management tasks. The other layer shown here represents the production system itself. Moving on. So throughout our work, we have used the NASA lithium-ion battery aging dataset. Now, this dataset contains various features that describe the physical and the output conditions during charging and discharging of a battery, like the measured current, the measured voltage, temperature, along with its observed capacity, obviously. So now, a popular method to predict the capacity of a battery is via a mathematical model. That is, we calculate the capacity of a battery after each cycle based on some selected features and applying some mathematics to it. So following is the graph here that compares the observed capacity of a battery with its calculated capacity. So the black point here, as you can see, these represent the observed capacity. The blue line here represents the model, that's the mathematical model calculations. So now we can see that the model predicts the capacity decently, but obviously there is a good scope for improvement that we have done in our work. So next, moving ahead. Understanding the calculation part that has been done to make the model, battery model, you can say. So the battery lifetime L here is the L here represents the battery lifetime, and it degrades after each cycle. So it degrades depending upon the linear degradation rate FD, which in turn itself is a function of charging time, depth cycle, cycle depth, cycle average state, and cell temperature. Therefore, the battery capacity is represented by C, which is defined as shown here in the slide. Now moving on. So now let's try to understand what exactly we have applied the ternary BA3+ model. So in the BA3+ method, the B represents the artificial neural network model, which is modified for the regression task. So the BA3+ employs only 3 individual Bs for each training cycle. And each iteration begins with these 3 initial solutions and as a forward pass of the model and continues with the specific searching strategies, including the local search, exploitation, stochastic gradient descent, which is stabilized by the singular value deformation, that is the SPD, and the explorative global search. So as with the basic Bs algorithm in the BA3+ model as well, the initial candidate solutions are sorted in the beginning. Now the 3 initial solutions that we have calculated here with the 3 Bs with the initial training parameter are sorted according to the loss functions. So the maximum fitness value that we get out of these 3 is selected as the fittest B, or we can say the best B, for the local exploitative search. And the worst fitness value that which we can say as third B is selected for the global search to avoid getting trapped at the local minima at any point. And the remaining B, that is the second B, is selected for the stochastic gradient descent learning with stabilization strategy of SVD operator to update the weights and biases of the model. So, and this optimization continues with new population of these, and this goes on until there's a stopping criteria that we have defined. So this is the overall BA3+ model that we have applied to the to our battery model to improve our predictions and get the results that you'll see in the next slide.
So now we have some amazing results to show, which we received after optimizing the model with BA3+ algorithm. On the left side, you can see a graph comparing the fitting of each of the 3 models: the model battery, that is the basic model; the hybrid model, which improves results of the basic model using a neural network; and the BA3+ optimized hybrid model, represented by the red line. You can see that the red line is the closest of all to the observed capacity data from the dataset. It's also evident if we compare the mean absolute error of all 3 models. BA3+ has a MAE value of 0.017, superior than any other model. Now, here you can see the graph comparing the future predictions made by all the 3 models. The BA3+ model is represented by the red line. The prediction, as you can see, like the predictions are by the BA3+ model are far compared to the other 2 models. Because it was better fitting the data set. They're better than the other 2 models. So in conclusion, with our work, we were able to optimize a hybrid model to estimate the battery state of health. One point to note is that our model gave better predictions by 32% than the non-optimized artificial neural network, even after using 50% less neurons. As like our BA3 plus model was built using 32 neuron architecture, while the artificial neural network was built using 64 neurons. And yes, in future, our proposed BA3 plus model could be connected to a physical entity for the digital twin.
Good morning, everyone. My name is Rashi Goel. I'm a third-year undergraduate student at Indian Institute of Technology, Kharagpur. Today, me and my teammate Shriya Harlapur, we will be presenting our research on the topic optimization of three-dimensional bin packing problem using an enhanced Bees algorithm. So let us understand firstly what is a three-dimensional bin packing problem. It is a combinatorial optimization problem that is strongly NP-hard, and it involves packing of boxes of different dimensions with efficient orientation in the least number of bins. So why we are using Bees algorithm for this is because it is a meta-heuristic algorithm that attempts to find the feasible solution in the polynomial time rather than the exact solution in an exponential time. It is a swarm intelligence algorithm that mimics the food foraging behavior of honeybee colonies, and it can be used for both combinatorial as well as continuous optimization problem. So three-dimensional bin packing aims to pack a given set of cuboidal items into minimum number of identical cuboidal bins with no overlapping. For this paper, we are using empty maximal space and distance to the front top right corner 2, that is EMS and DFT-RC2 approach that was first introduced by Goncalves et al. In 2013. So this is the first application of Bees algorithm in three-dimensional bin packing problem. We have built our solution based on the paper that uses Bees algorithm for one-dimensional bin packing problem by Hartono et al. 2022. So from here on, my teammate Shriya will take over.
Hello everybody, I'm Shriya Harlapur, a third-year undergraduate student from the Department of Mathematics at the Indian Institute of Technology, Kharagpur. And today I'll be taking you through the methods we've used to solve the 3D bin packing problem using the Bees algorithm. So first we encode the box packing sequence, that is the permutation of the n boxes that we have to pack into the B position, into the first half of the B position, and into the second half of the B position we encode the vector of box orientations. Once we have BPS and VBO, we place the boxes in the bins using the DFT-RC placement procedure, which I'll explain later. And after placing the boxes in the bins, we evaluate the fitness of this placement, and the parameter we've used here is the adjusted number of bins, which I'll explain again later. And after we've evaluated the fitness, the Bees algorithm takes its due course and updates the population and iterates until we find for the given number of iterations. As you can see, the parameters we've used for the Bees algorithm are 40 scout bees, 20 best sites, 8 elite sites, 10 recruited bees for the best sites, and 40 recruited bees for the elite sites. Before I move on to explaining DFT-RC, I'd like to explain what empty maximal spaces are. So assuming that this gray box in step 1 is the empty maximal space or the empty space that we have in a particular bin in order to pack a box into. What we do is we pack the box in the bottommost leftmost corner that we can find, and which you can see in step 2, and in step 3 we generate the empty maximal spaces that are a result of packing the box, which means that we generate the biggest cuboids that you can see in the box after this box is packed. As you can see, there are 3 empty maximal spaces generated in the bin after the box is packed. How does this play into the DFT-RC2 placement heuristic? What we do in DFT-RC2 is assuming that this light blue area here is an empty maximal space and that the boxes 1, 2 and 3 have already been packed. We now want to pack box 4 into this empty maximal space. what we do is we pack box 4 in all 6 orientations that are possible in 3D space. We pack this box into all the bottom leftmost corners, as you can see here, and we go ahead and pack them there, and we find the largest distance from the front top right corner. That's what DFT-ERC stands for. And so once we find the orientation and the placement that produces the largest DFT-ERC, we store that as the optimum placement. What we do is we try to find the largest DFT-ERC for all the possible packings of the box in every single bin, and when we find the largest DFT-ERC, we store that as the bin required. Now coming to the actual placement procedure, first we select the box using the Bayes algorithm and the box packing sequence that it has given us. Next we select the empty maximal space and the bin using the DFT-ERC2 algorithm, and we select the box orientation using the vector of box orientations in the Bayes algorithm, and we pack the box in the selected EMS as I've shown to you in the empty maximal space slide. And now we update the state information using the difference process by Lai and Chan. The reason we're calling this Bayes algorithm the enhanced Bayes algorithm is because it's assisted by the DFT-ERC2 algorithm, which is also a heuristic algorithm. I'm also going to explain how Lai and Chan's difference procedure works. So once you've placed the box in the empty maximal space, you generate the new EMSs that are produced, as I've shown to you in the slide about the empty maximal spaces, and you remove the empty maximal spaces that have infinite thinness in any direction, which means if any of its dimensions are 0, we remove it from the list of viable EMSs, and we also remove EMSs that are fully inscribed by other EMSs, which means that if an EMS is fully contained inside another, it's not really a maximal space, which is why we remove it from the list. Now that we have the updated list of empty maximal spaces, we choose the next box in the box packing sequence and repeat the procedure. The fitness function we've used here is the adjusted number of bins, where it not only takes into account the number of bins actually used, but it also takes into account the least loaded bin and the bin capacity, which is a measure of the fitness of the actual solution. Back to you, Rashi.
So now we came to the results and discussion. So for the proposed algorithm, we have used 200 iteration as the stopping criteria, and the number evaluation function for this proposed enhanced Bayes algorithm is 10 raised to power 7, while the biased random key genetic algorithm yields a result in a time of 10 raised to power 8. And the experiments which we have conducted, we have used the MATLAB 2020A in a Blue Bear supercomputer provided to us by University of Birmingham. So our initial result shows that the enhanced Bayes algorithm yields a better result, that is 10 times better than the BRKGA with a smaller number of NFE. So what are the takeaways from this workshop is that we have used the empty maximal space to manage the free space in the bins. Along with the Bayes algorithm, we have used another heuristic, that is DFT-ERC2, that is used to determine the maximal space where the box can be placed in a bin. We have compared our results with biased random key genetic algorithm, which gives the most promising result among all algorithm. But with Bayes algorithm, it have outperforms the existing BRKGA model. For the comparison, we have used number function evaluation so that we could scale down each algorithm on a common ground. For three-dimensional bin packing, we have used dynamically generated widely used industrial dataset since no standard dataset was available. Some of the applications of three-dimensional bin packing is that it could be used in loading cargo into the vehicles or the containers or the pallets, or for the packaging design. It could act as a sub-problem for the other packing problems or scheduling or cutting problems. So in this work, we consider that box can be rotated in 6 different orientations. And further work, we will use the more dataset and comparisons with the other algorithms. The rotated and non-rotated constraint for the box will also be covered in the future work. Thank you.
Hello everyone, my name is Satyam Kumar and I, along with my teammates Anurakt and Neha, worked on using the Bayes algorithm for hyperparameter search with deep learning to estimate remaining useful life of bearings, under the guidance of Ms. Nathini and Professor Pham. Now let's move on to the introduction. Bearing failures are one of the leading causes of failures in rotating machinery. Therefore, the accurate prediction of remaining useful life of bearing using the sensor data is very important. It is important to improve the reliability and decrease the maintenance cost. To solve this problem, we use deep CNNs and LSTM along with the Bayes algorithm to search for hyperparameters. The dataset which we used was from the IEEE PHM 2012 Prognostic Challenge, which had 5 training bearings and 11 test bearings. The evaluation metrics of the model is given here. Now moving on to the basic Bayes algorithm. Here the two slides will be a representation of the basic Bayes algorithm in the form of a flowchart. Starting with the flowchart, we set the parameters. Here N represents the number of scout bees, then NEP represents the number of bees recruited for the best E sites. Then comes E, which represents the number of best sites out of the M selected sites. Then NSP, which represents the number of bees recruited for the other M-E selected sites. And finally, NGH, which represents initial size of patches. The next step is the initialization step, where we generate initial population of N scout bees and then compute the fitness level of the patches. After this, the site selection process happens, where we rank and select the patches. This slide is the continuation of the previous slide, where we'll be continuing with the process. So the next step is to divide the process in 2 phases, namely local search, which is for the selected sites, and global search for the remaining sites. In the local search phase, a new solution is created for each employed bee through extrapolation crossover. That is, the employed bee is mated with a randomly picked partner and a new solution is generated. If the new solution lies in a position of higher fitness than the employed bee, it replaces the employed bee as the representative of the flower patch. For each patch, the same procedure is repeated for all the onlooker bees. In the global search phase, NS minus NB bees are placed randomly across the fitness landscape to scout for new flower patches. Random scouting represents the exploration effort of the Bayes algorithm. Now the final step is to update the fittest bee which is selected from each patch. These steps are repeated until a stopping criteria is met. Now moving on to the parameter reduction. Here we will be showing you the 2-parameter version of the basic Bayes. So the 2-parameter version of Bayes algorithm combines with the exploitative and explorative search capabilities of the Bayes algorithm. This allows us to reduce the number of parameters to just 2. So here the flowchart shows the algorithm and how it progresses. So I'll be explaining that. Firstly, the number of scout bees are set and the fitness of each of these patches is computed. The patches are then ranked according to their initial fitness values and bees are recruited to search. The best patches are searched more exploitatively and they are assigned more number of bees. The fitness of the sites are then re-evaluated and a check for the stopping criteria is performed. If the stopping criteria is met, the algorithm stops, else it continues to the next iteration. Now the use of 2-parameter version of Bayes algorithm in hyperparameter search. Hyperparameter optimization is one of the major challenges in deep learning, and we try to solve this problem using Bayes algorithm. And then we applied our own solution on a real challenge dataset. To use the 2-parameter version of basic Bayes, in a hyperparameter search, we first initialized the Scout Bayes n and built n models where the hyperparameters of each model are generated through a uniform distribution. In our deep learning model, there were 6 hyperparameters, namely number of filters, filter size, number of hidden units, dropout probability, initial learning rate, and mini batch size. We set the maximum and minimum values of these hyperparameters and generate them through a uniform distribution. After this, the 2-parameter version of Bayes algorithm exploitatively searches the hyperparameters, which produces the low losses and tries to tune those hyperparameters to find the best set of hyperparameters. As it can be seen from the graph, where the loss keeps on reducing till it reaches its minimum value after multiple iterations. Now moving on to the results that we obtained. So in the table shown here, we calculated the error of our model's remaining useful life estimate using the error metrics provided in the challenge. The final score of our model stands at 0.4261, which is 39.21% better than the challenge winning score of 0.3066. Now I'll be concluding our presentation. So the model produced as a result of the search produces better results than the challenge winner paper. This technique can also be used on other different models such as plain CNN, LSTM, or GRUs to find the best set of hyperparameters for training model. Thus, this hyperparameter search techniques shows potential to be applied in various domains of deep learning. Thank you, everyone.
First of all, also I would like to thank Professor Pham and Natalia and the chair for giving me the opportunities to present some of our work here. So my presentation, I would like to share with you about some of our progress, some of our work on the GBA for continuous and combinatorial optimization problem. Okay, so this is the agenda of the presentation. So I will share the GBA for continuous optimization problem, where we study on the machine learning. And then I will share about some 2 scheduling problem. So it's represented for combinatorial optimization problem. So the first one is the Tuesday assembly scheduling problem. And the second one is a just-in-time job shop scheduling problem. Okay, so the first one is the for the continuous optimization problem. And hopefully you can see something here in machine learning, and we have the B's here, and we have the GA, and actually we try to use the hybrid GA for MLP. And what is the motivation for this work? So actually, it's very interesting. So, and when I work in manufacturing, and so one of the things recently is there are many data. There are many data in manufacturing. And nowadays, more and more, they have data is very important for advanced manufacturing. And I get the contact with Professor Pham, and by these opportunities, I would like to thank Professor Pham for he giving a very good advice about how to move on the machine learning. And in addition, he also written a very seminar paper on some of the machine learning techniques and their application in manufacturing. And actually, I can still you to reference that. So for my study and some of my students study. And in the one of the things when we deal with the machine learning, so in machine learning, so there are different algorithms. So including MLP and deep learning and different algorithms like support vectors, machine, and recently deep learning is go very is a trend. So my student and I, we because we work with some companies and they have some data, and so we try to use the conventional machine learning techniques, try to optimize that. But as we know, so one of the optimization problem, the challenge for MLP, so they use the backpropagation technique, and because the reason that there's a lot of gradient descent, so and there's one problem for backpropagation, so they will have the local optimum trap. So so we try to move from that by using the meta heuristic. And so that's the reason. So we try to use the meta heuristic. And as I mentioned, so Professor Pham is a pioneer on the BAs, and I don't need to repeat that. But here, so we try, I get actually, when we try to solve different, in manufacturing, many hard optimization problems. So we need to do some hybrid, because as mentioned on the literature, so it is a very influential work. And he said that if somehow, if you can choose a combination of complementary algorithm concepts, and you can solve the many hard optimization problems, which in manufacturing, there are many NP hard optimization problems. So that is what also another my motivation why I choose hybrid. And as you know about the BA, and so we will start with try to hybrid BA with the conventional one is the GA. And also the reason is, as you present, so most of the, so we try to take advantage of the two algorithms and combine together. So for the BA, so it's very strong in local search, and so far there's many very work on that. But one of the disadvantages of BA is actually on the global search, and we mainly doing on the random search. So why don't we use the another algorithms to enhance the global search? So that is the motivation for this study. So we try to propose the this one is the hybrid algorithm. So this part is mainly on the BA, and this part is the for we hybrid with GA. So it's depend on some condition, and then whether it can do random search or can do the standard operators of the GA. And we try, because this problem is the continuous problem, and we try to optimize all of this weight and bias. Okay, and this is some of the, to evaluate the performance of the MLP, because this is we study the prediction problem. So we use the mean square error as the error rate. And for the start, so we use the simple function like the sigmoid function as our start. And so this one, we test it out with different GBA parameters. And And we also try compare with another algorithm like the PSO and then see, so is there any comparable solution quality between the two algorithms? Okay, and then we got, so to test on this machine learning algorithm, so we use different data sets and from UCI. So we choose from the simple data sets to a very difficult data set like the breast cancer. So we have the many training sample. So different level of difficulties on the data sets. And so this one is the conversion analysis. So just one example on the most typical data set is in the breast cancer. And we can see the conversion of GBA. So it depends. So they have depend on the number of iterations, and when it's at higher iteration, so there is the conversion of GBA. So it's comparable with the PSO. And then we also study some sensitivity analysis, because the swing factor is, when we study, we find that it could impact the performance of the algorithm. So we do some sensitivity analysis. And this one is the error rate, okay? And so then we do the comparison between the two algorithms, and we found that is quite comparable for all different data sets. Okay, so this one is our study on just a short summary on the continuous optimization problem. And we find that, so with the GBA, so we can improve the solution exploration, and it could be proven to be a successful strategy for training the MLP, and can we achieve the lower error rate. But as I mentioned, so now recently, so we are going more into deep learning. So in the future work, so we may consider to improve the algorithm and to test on the deep learning structure. So this one is for the continuous problem. And then, so after that motivation, so in manufacturing, so one of the things is, on the, we have many combinatorial optimization, especially on the scheduling problem. So, so we work on another two problems on combinatorial optimization. So the first one, we call two-stage assembly scheduling problem. And this is the layout, on the two-stage. Here we have a two-stage of assembly scheduling problem. So you have the stage one, it could be machining, and you have different job, and you have different machine. And in stage two, so after you do different components, so you can assemble together. And this is the two-stage assembly scheduling problem, is the NP-hard problem. So when the size is increasing, so it's very difficult to solve with the the exact method. And this application, there is actually many applications in manufacturing. For example, in the personal computer manufacturing and many manufacturing, if you have two stages. And one of the objective is we will try to optimize what we call the max span and completion time of jobs. Okay, so that we can save time and cost for production and labor and so on. So this is the objective. And when we solve this problem, so this is the mathematical model for this problem. And here so this is a Cmax. So this is some of notations. And if you are working on the scheduling problem, so you will familiar with this. So basically it's about number of jobs, number of machine. But for this study, one of the things is, so most of the scheduling, they do not take into account the setup time. So in this study, so we also do consider the setup time for the for the operations. And here, so we try to, we have the Cmax and we have mean completion time. So the mean completion time up on the job. And the objective function is we try to, actually there are two objectives, but we try to combine into a single objective we call Apple Max, and it depends on the weight. And we, in the scheduling problem, so we try to find the sequence of the jobs so that we can minimize this function. So that is why it's the combinatorial optimization problem. And for the first study, so actually in the scheduling literature, so I find that, so this is actually also from Professor Pham and Professor Yu's group. So they use also the GPA, but this one for the single scheduling problem. So our study, the problem is different, but we try to try first with this GBA algorithm. And we can see from here, actually the GBA, so we try to improve the global search by reinforce and jumping function. So the more details of this, so you can do reference to in this paper. And we also to test with different parameters on the jobs and machine and so on, and the data, actually we use the benchmark data. And so for the data for the BA algorithm, so we also to use from Professor Yu's paper from the beginning. And to evaluate the performance, so we use what we call the average percentage error. So if it is small, that will be better. So average percentage error is just this difference. And this one, if you run and you have the best solution at high run, and then if the smaller is the better. And it is some of the experimental results. And we can see that, so this, the blue line here is the GBA. And we also do some comparison with the GA and PSO. So in terms of the APE, so we can see that, so GBA provide the best APE for the three algorithms that we test. Even though we find the PSO is the worst, but maybe this one is not the latest version of PSO. So, but because it's the first study. So another one is another challenge is when it's for the combinatorial optimization problem, when the size is increased. So in this example, the number of jobs increased. So we find that the running time of GPA is again, we can see from here, is longer than GA and PSO. So because of the, we do a lot of operators here. Okay, so this was this. So for this work, so GBA, we can achieve a lower percentage error than GA and PSO. But however, when we try with the large size, so the runtime of GBA is longer than the other conventional one. So in the future work, so we may also consider to solve maybe a three-stage assembly scheduling problem. So I hope I have some time, and I would like to share, well, maybe this one is a recent work, and we are still working on. Is it okay if I still have time?
Professor, you still have the time.
Sorry? Okay.
Yes, Professor, you can continue. We still have the time.
Thank you so much. Okay, so so this is a recent work. So we call, so we try the reason. So in manufacturing, there is another concept. If you in the manufacturing, we call lean productions. And just in time is important, ideas in the lean production. And for the conventional job shop scheduling, it's a conventional job subscheduling problem. But now if we consider just-in-time job subscheduling problem, so we can consider both the, just the time factor in the job subscheduling problem. So I just give you so the motivation for this just-in-time job subscheduling problem is, first of all, the job subscheduling problem is a flexible. If you want to come in manufacturing, it's a type-based competition manufacturing. So we need to focus on the time. And job shop is provide you very flexible scheduling. And this job shop scheduling is mainly we apply for very complex manufacturing, such as semiconductor manufacturing, which I used to work before, and we use job shop scheduling. So I just give an example here. So in the job shop scheduling problem, so this is an example of we have 4 jobs and we have 3 machines. But in just in time, so not only we consider the scheduling and sequencing of jobs, so we also consider the time factor we call earliness and tardiness penalty coefficients. So if some job, so they have a certain due date, and if a job is finished earlier or finished late than the due date, so it will create different penalties. Okay, so this one is example of the Gantt chart for the scheduling problem. And so this one is the model for the just-in-time job scheduling problem. And so if you're again working on the scheduling problem, so you will familiar with this. So I don't have time to go into the details of this notation, but basically, so we try to minimize, this one is the objective functions. So we try to minimize the sum of earliness and tardiness for all the job. And so this one is on different constraints. So because all the jobs and all the machines, so they have the constraints on the sequence and also constraint on the machine. And this one is the earliness and the tardiness constraint. And this one, we make sure that the earliness and tardiness is positive.
Professor, so we have 2 minutes left.
Okay. So with this mathematical problem, again, so we try also first on the GPA. Okay. And so this one, so we try with this parameters. And so this one is just our initial result. Actually, we just got a few days ago. And for this condition, so we have 10 jobs and 2 machines. So we call the small sign. And then, so this one is the objective function. And we compare that with this one is the 3 state-of-the-art meta heuristic. So for the small size, so for this instance, so it's comparable. But when the size of the machine is larger, so our solution, this is our first test, and the iteration is currently we run only about 108 iteration, and the time it takes is quite long. So it haven't achieved the optimal solution yet for the larger size. So this one is when the size is larger, so we also cannot achieve the optimal solution yet. because for every instant, it takes quite a long time to achieve that. So this one is, we just get the result thing last week. Okay.
Sorry, Professor, 1 minute.
Yeah, so it's the end. So GBA is a summary of future work. GBA provide comparable solution quality from this study. And so in the future work, so for the large size problems, so we need to do more improve on the computational time. And actually, we also need to do different optimization of parameters. And for the job shop scheduling problem, so one of the things we need to improve further is the initializations of the solutions. And we try to do some local search improvement to improve the result. Okay, so with that, but by the way, I also take this opportunity and really appreciate Professor Pham for providing me many valuable advice. And also some of my students and colleagues has contributed to this study. Thank you so much. And I'm happy to answer any questions.